As we mentioned in the previous video, the color change for an indicator happens over a pH range. And so the color that you're going to observe is going to depend on the position of the equilibrium, which is related to the ratio of the indicator in its deprotonated and protonated forms. So let's take a look at what's happening on either end of this transition range and what's happening in the middle. So on one end of the spectrum, if I have a situation where that ratio of the deprotonated to protonated form of my indicator is 0.1, meaning that the protonated form, the concentration is 10 times greater than that of the deprotonated form, that means that the protonated form's color is going to be predominant. Okay, and so if we use the Henderson-Hasselbalch equation, we can see that this corresponds to a pH that is one point below the pKa for the indicator. So at a pH 1 below the pKa for the indicator, that means that the protonated color is going to be predominant. On the other end of the spectrum, if the ratio is 10, meaning the concentration of the conjugate base of the indicator is 10 times greater than the protonated form, that means that the deprotonated color is going to be predominant. And if we see using the Henderson-Hasselbalch equation, this corresponds to a pH that is 1 point greater than the pKa of the indicator. So if the pH is 1 point greater than the pKa or greater, then the deprotonated color is going to be predominant. Now everything in between, all those ratios between 0.1 and 10, there's going to be an observable color change that happens as the equilibrium shifts in the response to acid or base. But right in the middle, when those concentrations of the conjugate base and acid for the indicator are equal, that ratio is 1, that means that the pH is equal to the pKa, and this is what the transition point is defined as. And so when we go and we're going to go do a titration, we want the pKa of our indicator to be within 1 unit of the pH at the equivalence point. Okay? Remember, the equivalence point and the transition point are happening independent of each other. The equivalence point, the pH at the equivalence point is depending on the reaction in the actual titration itself. So it's our job to choose an appropriate indicator where the transition point is corresponding with the pH at the equivalence point. And so we can use our data pages to predict the pK of an indicator by simply averaging the lower and upper pH values for the indicator. So for example, if we look at our data pages and we look at bromothymol blue, you can see that it has a pH range of 6.0 to 7.6, where it's going to be changing colors. So at a pH below 6, that means that the yellow protonated form of this indicator is going to be predominant. So at a pH below 6, we're going to see yellow. At a pH above 7.6, the deprotonated form is going to be predominant, and we're going to see a blue color. Now at pHs between 6 and 7.6, we're going to be seeing a color change. And so we're going to see a mixture of a yellow and blue color. Now when the pH is 6.8, which is the average of that pH range, 6.0 plus 7.6 divided by 2 is 6.8. That means that that is the pKa for the indicator, and so that will be where the transition point is occurring. At this pH, we should see an equal mixture of yellow and blue, and so we'll see kind of a greeny color for this indicator.